Welcome to the next lecture of wireless communication. In this short lecture, we will try to introduce about the various multiple access techniques which are used in multi-user wireless communication scenario. Okay, so here are the various multiple access techniques which some of you might have come across. One is the frequency division multiple access, time division multiple access, code division multiple access, and then some of the recent techniques. One of them is OFDMA, orthogonal frequency division multiple access, and non-orthogonal multiple access. We will in detail study first three, and we will give some brief introduction of the last two multiple access techniques. So frequency division multiple access, most of you might be aware that in we call it FDMA. We have a lot of independent signals which can be combined into composite signal for transmission over common channel. Let me give some example here, what it means actually. See, I will first introduce a notion of orthogonality in general. Orthogonality. Okay, let me give a motivation for it. Suppose you have user 1 and you have user 2. They both want to communicate simultaneously with the receiver, okay, Rx. Now if they will, suppose user 1 transmits this information, sine of 2 pi ft. This is the signal which will be transmitted by user 1, and this is A1 A2 sine 2 pi f2t. This is the signal transmitted by user 2. So as you can see, sorry, let's say it is f, same, okay, f. Now what you see is that if they simultaneously at the same time, if they transmit these signals to the receiver has no means of differentiating that whether this signal came from user 1 or user 2, okay, because they have same frequency. Now what will be the how can we benefit if we take different frequencies? Suppose this is f1 of t, this is f2 of t. Okay, so what receiver receives is both A1 sine of 2 pi f1 of t plus A2 sine of 2 pi f2t. Now from this combined signal of user 1 user 2, receiver has to identify which signal is of user 1 and which signal is of user 2. What is the information given to receiver? What receiver knows? Receiver knows that f1 is the frequency of user 1 and f2 is the frequency of user 2. Okay, this much information receiver has. Okay, now a simple operation which receiver can do, that is called correlation operation. So what correlation means, that suppose you represent this as y of t, okay, so receiver will do y of t just a minute. Sorry, yeah, now y of t, and it will multiply it with first sine 2 pi f1t and integrate it for some time period t. Okay, so what you will get is, you will get two terms. One will be containing sine square 2 pi f1t, right? I will just write those two terms the other will be sine 2 pi f1t sine 2 pi f2t. Okay, so this term sine square 2 pi f1t, this will be you can convert it into the standard form 1 plus cos 2 theta, and you will get so what is multiplied here is suppose a1, right, and what is multiplied here suppose it is a2. Okay, so this term you will see that this term will depend upon what is the value of f1 minus f2. Accordingly it will be 0 or non-zero. How? Basically you can use this sine A sine B formula, okay, which will be some cos of so it will be 1/2 of cos of a plus b by 2 plus cos of a minus b, sorry, it's cos of a plus b cos of a minus b, something like this. So then accordingly this integral will be 0 depending upon the particular values of f1 minus f2. Okay, it's a small exercise, you can try it. What is the overall moral of this? What I want to say, if two users use different frequencies f1 and f2 and they are separated by a particular amount, the f1 f2, that is f1 minus f2 is not arbitrary, rather they are separated by a particular frequency such that this second integral is 0, then receiver can easily get signal of each user, right? So first it did the correlation of received signal with carrier, or we can say frequency of first signal sine 2 pi f1 t, you got the signal equivalent to what was transmitted by user 1. Similarly, if receiver does y of t sine 2 pi f2 t dt, then with this operation receiver can get the signal corresponding to the second frequency, that is second user. Okay, so this was just a brief, you can say a mathematical explanation why we go for frequency division of multiplexers and what does it mean. Number of independent signals. Now here f and f2 are two different frequencies, they are two independent signals, can be combined into a composite signal suitable for transmission over common channel. Now this y of t, you can think of composite signal, right, which we have transmitted over it, right? Sorry. Okay, so that is what it means. Now since we know that voice frequencies, they range from 300 hertz to roughly 3 kilohertz, and to transmit number of such voice signals, then the signals must be kept apart so that they don't interfere with each other, right, and they can be separated at the receiver end. So this can be accomplished by separating the signals either in frequency or in time, right? The technique of separating signals in frequency is referred to as frequency division multiplexing, and the separate technique of separating the signals in time is called time division multiplexing, right? So like this, suppose this is the time axis, okay, and what you do is, suppose there are only two users, so you allocate some time period capital T. First time you allocate this to user 1, then to user 2, then to user 1, then to user 2, so on and so forth. So receiver knows that in the first time slot the signal corresponds to the signal of user 1, then it corresponds to user 2, then it corresponds to user 1, and so on and so forth, right? So this is called time division multiplexing. Okay, and what I showed you before is frequency division multiplexing, where we are allocating different frequencies. The different frequency bands allocated to different users are separated by God bands to avoid the interference between them, right? So suppose you cannot keep f1 and f2, that is what I was saying, arbitrarily apart, right? You have to keep a specified gap, otherwise there will be interference. That is when the receiver will try to decode signal of user 1, he may get some portion of the signal of user 2 also, and vice versa. So to avoid that, you need to put some gap between the frequencies, and those gaps should not be arbitrary. Okay, they need to be calculated, and this is called God band. Okay, this much gap. Sorry, the incoming message signals are assumed to be low pass type, but their spectra do not necessarily have non-zero values all down to zero frequency. So low pass, I have told you already. So all the message signals, they have their spectrum something like this. Their spectrum lies near the zero frequency or in the low frequency range. We call this low pass signals. Okay, low pass signals. These are, your baseband signals are all low pass signals. Baseband. Okay, usual natural voice signal, video signal without modulating, you can say. Now, following each signal, low pass filter is used to remove high frequency components that do not contribute significantly to signal representation but are capable of disturbing other messages that share the common channel. See, this is very common in speech. Suppose if you see a particular speech spectrum, okay, suppose speech, right? You may see something like this. These small lobes may go, it can go up to 20 kilohertz, as all of you know. That is the maximum audible frequency. But the significant part will be almost within 4 kilohertz. Okay. So what we should do is we can put a low pass filter over here. Low pass filter, right? So these may unnecessarily in fact create interference. So we'll just get rid of most of the information in our voice signals that's contained in this range. So that is what it means, that we first use low pass filter to remove that unnecessary high frequency components. These filters may be omitted only if input signals are sufficiently band limited. Okay, and filtered signals are applied to modulators that shift the frequency range to signals so as to occupy mutually exclusive frequency intervals. Let me just in the notion of digital communication, let me give an example about it. That suppose you have two voice signals and you convert them into non-return to zero type of signals, NRZ, right? This is now digital signal correspond to user 1 and the second one is corresponding to user 2. Now what you can do is, if you want to use frequency division multiplexing, so you can use suppose BPSK, but here for user 1 you can use cos of 2 pi f1t as carrier, and here you can use cos of 2 pi f2t as carrier, and f1 minus f2 gap should be maintained in a very sophisticated way so that there is no interference, and you can transmit these two modulated signals simultaneously over the same channel. That is the power of frequency division multiplexing. That is what it means, that we will modulate it. Okay, the necessary carrier frequencies needed to perform these frequency translations are obtained from a carrier supply. Definitely we will have sort of a bank of oscillators which can generate frequency of different signals or sinusoidal signals of different frequencies. If the information source is analog voice, then a common method of modulation used for frequency division multiplexing is single sideband modulation. So if you want to go for analog modulation, suppose, then we go for single sideband, okay, SSB modulation. Now in case of voice, each voice input is usually assigned a bandwidth of 4 kilohertz, as I have already told you. We don't go for 20 kilohertz. Significant information in voice is contained within 4 kilohertz. The band pass filters following the modulators are used to restrict the band of each modulated wave to its prescribed range, already explained. And then the resulting band pass filter. Okay, now this is the band pass filter of modulators, right? So that needs some attention actually. See, first is the low pass filter. We apply that to the message signal. Okay, now we got that. After that we translate this, suppose, to the higher frequency range, right? But here also we may have some unwanted spectrums here. Okay, so we will put here band pass filter. By putting band pass filter, we will again, if there is some unwanted signal which can create interference, we get rid of that. That is what it means, that band pass filter following the modulators are used to restrict the band of each modulated wave to its prescribed range. And further, there is another reason for using band pass filter. Suppose user 1 is operating at frequency f1, user 2 is operating at f2, so I will use a separate filter for other user. Okay, so that is also the reason for using band pass filters. And then the resulting band pass filter outputs are combined in parallel to form the input to the common channel. Okay, so then we transmit it simultaneously over the common channel. At a receiving terminal, the bank of band pass filters with their inputs connected in parallel is used to separate the message signals on frequency occupancy basis. Finally, all messages are recovered by individual demodulators. Okay, see what it means. Let me just give some simple example. Suppose I will take example of 2 user only. Okay, suppose user 1 you modulate at f1 frequency, user 2 you modulate at f2. Okay, nice. Now suppose this is the spectrum and this is the spectrum. Okay, this is a spectrum, this is a spectrum, right? So you first put this band pass filter, you get the signal of user 1, you put band pass filter here centered around f2, you get signal of user 2. Then you are basically multiplexing them, combining them and transmitting over the same channel. Now at the receiver, what you need to do, at the receiver you'll again get now combined signal, right? So that is in terms of frequency, you will get both f1 and f2. So definitely at receiver also you had to put several band pass filters. So one band pass filter centered around f1, you will get user 1 signal. Other band pass filter centered around f2, you will get user 2 signal. That is what it is saying here. Okay. Okay, now we have to see that this FDM, that is frequency division multiplexing, it operates in one direction. What does it mean one direction? That is, we are doing it at the transmitter. So a transmitter can only transmit, it can't receive, right? So it can transmit using frequency division multiplexing, receiver can receive only, not vice versa. Now for two-way communication, suppose in case of telephones, we need to duplicate this multiplexing facilities. That is, we need transceiver at transmitter as well as receiver. So that is, your telephone should have this multiplexing as well as demultiplexing options. Okay, sorry. So now in next lecture we will further elaborate on this frequency division multiplexes and also introduce the promising and what was responsible for the third generation mobile communication, we can say, revolution, that is CDMA, code division multiplexes. So in next lecture we will have some more details about FDMA and some more figures also, and also briefly I will introduce TDMA. That is also very easy and simple, and then the actual goal is to study CDMA, okay, which was responsible for high data rates provided in the 3G mobile communication. Okay, so that is it for today's short lecture about multiplexing. Till then, bye.